Rajasri, Assistant Professor, Department of Electrical and Electronics Engineering, working at MLR Institute of Technology, Hyderabad. And in today's lecture, let us first see Introduction to Inverters. Firstly, what is the purpose of an inverter and what does it do? Basically, an inverter, it converts DC supply to AC supply. And what is the source of these particular inverters? The source may be a battery source, or otherwise output of an rectifier will be fed as an input to the inverter. And what are the applications of these particular inverters? It can be used in induction motor drives, uninterrupted power supplies, as well as induction heating and standby power supplies. So these are the various applications of these particular inverters, and the output voltage of inverters can be controlled by the drives of the switches. Switching accordingly, we can actually control the output voltage of these particular inverters. And here, the output of the inverter, it can be a square wave, quasi-square wave, or distorted sine wave. It can be anything of these. And then here we'll be making use of PWM converters. PWM. What is PWM? It is nothing but pulse width modulation, and it is actually used in order to control the output voltage of the inverters. And if you see, the output voltage of the inverter may not be sinusoidal, and because of which certain amount of harmonics will be induced in the system. And you know very well, if at all if harmonics are induced in the system, in that case the losses will be increased, and in this process heating will be increased, heating of the concerned appliances will be increased, and because of the because of these losses, heat losses, efficiency will be coming down. And in order to avoid all these disadvantages, we'll be making use of such type of switching techniques, so-called PWM techniques, pulse width modulation technique, and thereby control the output voltage, and we try to maintain that near to sinusoidal such that harmonics will be reduced. So that is the only idea. The respective triggering pulses for these particular transistors will be generated such that the output will be near to sinusoidal, and we can reduce the harmonics in this process. So that is all about the PWM techniques which we are going to see here in inverters. And we'll be having both voltage source inverters as well as current source inverters. Voltage source inverter, that means the voltage when the input to this particular inverter is constant, input voltage to this particular inverter is constant, then we call it as voltage source inverter. And if at all current input to this particular inverter, if it has remained constant, we call it as current source inverter. And here DC input to the inverter is controlled to adjust the output voltage, and we call these as variable link DC voltages. And here from inverter we can obtain single phase or otherwise three phase output. And firstly, let us discuss half bridge inverter. Half bridge inverter, it consists of two transistors basically. And here the moment when we provide the base drive. See, this is the base drive for the transistor 1, IDT1, and this is the base drive for the transistor T2. And when base drive is provided for the transistor 1, that is right from the instant 0 to T/2, at that instant here our transistor 1 will be switched on, and it starts conducting current through the load in this direction. That is from the point A to B. And here the current remains positive. And if you see, let us observe the output voltage waveform, and this is the output voltage waveform. And the moment when we switched on the transistor 1, at that instant voltage will be appeared across the load from 0 to instant so-called T/2, and the moment T/2 reaches, here we have withdrawn the base drive for the transistor 1, That means now transistor 1 is turned off, and at this moment called T by 2, we have provided the base drive for the transistor 2. And because we have provided the base drive for the transistor 2, now here transistor 2 is now turned on and it is conducting a current through the load in this direction. And this is the current flow through the load right from B to A. That means here negative half cycle of the output voltage is appeared because current is flowing in the reverse direction to that of the first case, and that is how we are obtaining the negative half cycle of the output voltage, and that is appeared right from the moment when we provided the base drive for the transistor 2, that is from T by 2 to T. And now at this instant called T, again we have provided the base drive for the transistor 1. And so what? Transistor 1 again starts conducting current through the load from A to B. And so what? Positive half cycle of the output voltage is controlled. And if you see, input is DC, which is unidirectional in nature, whereas output is AC. It has got both positive half cycle of the output voltage as well as negative half cycle of the output voltage. And this is how we are obtaining inverter which converts DC to AC. And if you see, the magnitude is upper half, it is Vs by 2 of magnitude Vs by 2, and in the lower half it is Vs by 2, and lower half it is minus Vs by 2. So this is the amplitude of the output voltage waveform. And now talking about the output current, and if you see, output current is just similar to that of the output voltage because this is resistive load. And here output, the moment when we provided the base drive, current started flowing through the load. That is how we are getting current right from 0 to T by 2 because transistor 1 is conducting in this period. And the moment it reaches T by 2, we have withdrawn the base drive. So what? Transistor 1 is turned off and we have provided the base drive for the transistor 2, and that is how we are getting the output voltage waveform right from the instant T by 2 to T. And this is due to transistor 2. And again transistor 1 is turned on, and so what? We are getting the output voltage right from this instant till here because of T1. And this is all about the output current waveform. And now current through the transistor 1, and the moment when, as long as transistor 1 is conducting, we will get the waveform across the transistor 1. And if you see, we are getting the waveform right from 0 to T by 2. This is the current through the transistor 1. As long as transistor 1 is on, as long as we are providing the base drive, as long as transistor 1 is turned on, we are getting the current through the transistor 1 and with amplitude Vs by 2R. Vs by 2R. And then again from instant T by 2 to T, we have withdrawn the base drive for the transistor 1. So what? Transistor 1 is turned off. That means there is no waveform or current through the transistor 1. And the moment when it reaches T again, here we have again provided the transistor 1 base drive. So that is the reason transistor 1 is turned on, and so what? It is conducting a current through the load, and this is the current because of transistor 1 from this instant to this instant. And if you talk about the current through the transistor 2, the moment when we provided the base drive for the transistor 2, it is conducting, and remaining time it is off. So this is the individual circuit diagram when transistor 1 is conducting current through the load with magnitude Vs by 2, and this is the individual circuit diagram when we are providing the triggering pulse for the transistor 2, and it is conducting during the other half cycle with magnitude Vs by 2. So this is all about the half bridge inverter where it consists of only 2 transistors. Now let us observe the waveform for half bridge inverter with inductive load. So here, when this is the base drive which is being provided for the transistor 1, and this is the base drive which is provided for transistor 2, and this base drive for the transistor 1 will be provided right from this instant called 0 to t by 2, 0 to t by 2, and again from this instant called t to this instant. At these both instants, we are providing the triggering pulse for the transistor 1 or base drive for the transistor 1. And at that instant, the moment when we have provided the base drive for the transistor 1, at that instant transistor 1 gets turned on. And here transistor 1 is conducting current through the load and back to supply. So when transistor 1 is actually conducting, see here from this instant called 0, we have provided the triggering pulse for the transistor 1. So what transistor 1 is conducting and how long? Till the moment we have withdrawn the base drive for the transistor 1. There is no base drive, so that is the reason this has come down to 0, and this is nothing but the output voltage waveform. And it has, since this is half bridge inverter, only half of the voltage will be appeared across the upper half, and so what with magnitude Vs by 2. So that is the reason the output voltage magnitude now it is Vs by 2 from 0 to t by 2. And the moment it reaches t by 2, here we have withdrawn the base drive for the transistor 1 and we have provided the base drive for the transistor 2 instead. So that is the reason transistor 2 is conducting right from this instant t by 2 to instant so-called t. So now transistor 2 is conducting. And again at this instant transistor 1 base drive is provided. So what transistor 1 is conducting from t to this instant. And if you see, when transistor 1 is conducting, current is flowing right from A to B. So what? We are getting the positive half cycle of the output voltage control. And let us examine the same for transistor 2. When we provided the base drive for the transistor 2, at that instant current is flowing through transistor 2 and again from B to A. B to A in the sense current is flowing in the reverse direction to that of the first case. In the first case, current flown from A to B. Whereas in the second case, current is flowing from B to A. So that is how we are getting the negative half cycle of the output voltage control. So what? When we provided the unidirectional input, that is DC, which is a straight line, whereas output of the inverter has got both positive half cycle as well as negative half cycle of the output voltage. And this is how we are able to convert DC to AC. And now, if you see, the moment when transistor 1 is conducting, let us examine the output current waveform. Output current waveform, this is I0. This is I0. And here, current started building at a slow rate. Why at a slow rate? It is because of the presence of an inductor in the load. And inductor has got an inherent property which does not allow any sudden changes in the current. So what? Current is building at a slow rate and this current is flowing through the load just because of the transistor 1. Just because of the transistor 1. So it is building at a slow rate and it became maximum at this instant called t by 2. And the moment it reaches t by 2, we have withdrawn the base drive for the transistor 1. So what? Transistor 1 is turned off, and once it is turned off, but when transistor 1 was conducting, inductor has stored certain amount of energy. So that is the only reason it tries to maintain the current flow in the same direction. So what? It tries to forward bias D2 such that current will be flowing through the load in the same direction, that is from A to B. So what now? Whatever the energy stored in the inductor is dissipated through the load, and because it is providing the energy from the inductor, the energy stored in the inductor is getting reduced, and finally at this instant called T2, the current through the load has become 0. And now at this moment, if you see, right from this instant called T by 2 itself, we have provided the base drive for the transistor 2. So what? Transistor 2 is conducting current through the load from B to A. So that is the reason Now current through the load is building at a slow rate in the negative direction. Why is it in negative direction? If you observe, current flow because of T2 is from B to A, which is in the reverse direction to that of the first case. So what your current is building at a slow rate in the negative direction, and the moment it reaches T, when since we have withdrawn the base drive for the transistor 2, now transistor 2 is turned off. Transistor 2 is now turned off, and at this instant, because there is still certain amount of energy present in the inductor, and as it tries to maintain the current flow in the same direction, so what it tends to maintain, it tends to forward bias D1, it tends to forward bias D1. So what, the D1 switch is on, and now current is dissipating through D1 to load. So that is how here current is getting reduced through the inductor, and ultimately it is becoming 0 at this instant. And now again current is building at a slow rate because we have provided the triggering pulse at T itself to the transistor 1. So what, by the time the current through the load is 0, now T1 came into picture and it started conducting current through the load, and by the time it reaches maximum value, we have removed the base drive, and whatever the energy stored in the inductor is still maintained conduction through D2. And the cycle repeats. So this is all about the output current, and talking about the supply current waveform. And if you see supply current, even when T1 is conducting current through the load, there is a supply current. Even when inductor is dissipating current through the diode, there is a path through supply. In all the cases, when D2 is conducting, there is a current path through supply, and even when T2 is conducting, also there is a current path through supply. So that is the only reason in all such conditions it is actually driving the current from supply as well. So that is the only reason. Here this is the supply current waveform when transistor 1, 2 as well as diode 1 and 2 is conducting. So this is the supply current waveform. Now talking about the individual current waveform across transistor 1. If you see transistor 1, it is active right from this instant to this instant. So what, here I am indicating the current waveform through transistor 1, and again here transistor 2 is conducting, so there is no waveform across the transistor 1, and again at this instant called T1, here transistor 1 again came into the picture. This long transistor 1 is conducting, so what, I have indicated the waveform across transistor 1. And now this is the waveform through the diode 1, as long as diode 1 is conducting. When the diode 1 is conducting, here it is conducting diode 1, here it is conducting, as well as here it is conducting D1. So that is the reason in both the cases we will have to indicate the waveform across the diode. And this is all about the half bridge inverter with inductive load. And let us observe the RMS value of output voltage. Let us derive the expression for RMS value of output voltage. Here V0 RMS is equal to, it is given by the general formula 1 by T 0 to T V0 square of omega T d omega T whole to the power of 1 by 2. And here if you see, the limits are, it was conducting from 0 to T by 2 with the magnitude Vs by 2 whole square d omega T, plus it is again conducting from T by 2 to T minus Vs square minus Vs by 2 whole square d omega T, and this is whole to the power of 1 by 2. So that means let us bring out the constant. In that case we get Vs by 4T, and integrating T And substituting the limits, we get t by 2 minus 0 plus upper limit minus lower limit, we get t minus t by 2. In that case, here t by 2 and this is t by 2. In that case, we get t and that t gets cancelled, whole to the power of 1 by 2. In that case, we get V naught RMS is equal to Vs by 2. And this is the RMS value of output voltage expression. That is, V naught RMS is equal to Vs by 2 for a half bridge inverter with RL load. In the upcoming lecture, we'll be seeing full bridge inverter. Thank you.